So we've learned how to calculate determinants. We've seen some algebraic applications of determinants. And now I'd like to say just a few brief things about the geometry of determinants. So let's jump right in. So one thing that determinants could do for us in 2 dimensions is establish what's called orientation. So here's the technical definition. Let's say that we have a list of vectors v and w in R2. Every list of this form, so every list of 2 vectors in R2, falls into one of 3 categories. The first category is positive orientation. What this means is that if we plot our 2 vectors so that they emanate from the same point, and we rotate the first vector on the list, in this case v, through the angle that gets us to w shortest, that rotation is counterclockwise. So positive orientation means rotation from the first vector to the second vector is counterclockwise. Negative orientation is the opposite. Negative orientation means to get from the first vector, so v, to w, we go through a clockwise rotation. So we could be positive orientation, we could be negative orientation, and the third category is what's called collinear. The idea is that if our 2 vectors are parallel, there is no angle to pick, right? So for this example, v and w point in the exact opposite directions. So it's not clear if we were to rotate v to w, if we would go clockwise or counterclockwise. In this case, we say the 2 vectors are collinear. And this is exactly the case in 2 dimensions when the 2 vectors are linearly dependent. So any 2 vectors in R2 are either positively oriented, which means counterclockwise rotation from the first vector to the second vector, negatively oriented, which means clockwise rotation from the first vector to the second vector, or collinear, which means linearly dependent. And it's important to note here that the order of the list is crucial in establishing orientation. The fact that we're viewing v as the first vector in this list is absolutely necessary in order for us to establish notation. If we were to reverse the order here, instead study the list wv, then in the first figure here, we would actually be looking at a negatively oriented list. And in the second figure here, we would be looking at a positively oriented list. So switching vectors will change the orientation. Okay, so now let's see how determinants fit into this idea. So let's say we start with 2 vectors in 2 dimensions, v and w, and let's use those 2 vectors to define a parallelogram called fancy p here. Well, it turns out that if we put those 2 vectors into the columns of a matrix to form a 2 by 2 matrix, the sign of the determinant of that matrix tells us the orientation of the list v comma w, and moreover, so if the sign of that determinant is positive, that list is positively oriented, and if the sign of that determinant is negative, then the list is negatively oriented, and if the determinant is 0, that means the 2 vectors are linearly dependent. Furthermore, the area of the parallelogram is the absolute value of this determinant. So what we're finding here is that in 2 dimensions, the determinant will tell us the orientation of the 2 columns of our 2 by 2 matrix, and the absolute value of the determinant tells us the area of the parallelogram formed by those 2 vectors. So let's see an example here. Let's say we're studying the vectors v equals negative 391, 760, and w equals 881, 696. Well, I can put those 2 vectors into the columns of a matrix and take the determinant, and when I do that here, I get negative, 941,669. So I get a large negative number here. What does that tell me? That tells me that v comma w is negatively oriented. So when I construct my parallelogram here, I was careful to make sure that the angle was clear enough so that if we rotated the first vector v to w, the direction of rotation would be clockwise, because that's what negative orientation means. Moreover, what is the area of this parallelogram? Well, the area of the parallelogram would be the absolute value of this determinant, which would be 941,696. So in 2 dimensions, we can use determinants to establish orientation, and we can use determinants to calculate area of a parallelogram.